The morning mist clung to the testing grounds as Major Klaus Hartman raised his field glasses toward the concrete barriers stretching across the landscape. It was September 20th, 1943, and he stood at the Ryan-Metall Borsig proving ground in Germany, watching something that seemed to bend the very rules of warfare itself. Chief Engineer Karl Warninger stood beside him with the calm assurance of a man who had spent years turning the impossible into reality. Below them, a German soldier crouched in position, his STG-44 rifle fitted with something extraordinary. A barrel that curved at an impossible angle. The attachment looked like nothing Hartman had ever seen in 3 decades of military service. The rifle erupted with fire, smoke billowed across the range. But what happened next defied everything military doctrine had taught them. A target positioned around the corner, completely hidden from the shooter's view, exploded into splinters. The soldier never exposed himself. He never even saw what he was hitting. Yet the bullets found their mark with devastating precision. Hartman lowered his glasses slowly. For years, every soldier in the Wehrmacht had learned the same brutal lesson. If you wanted to kill an enemy around a corner, you had to step out and expose yourself to their fire. It was a tactical reality that had turned urban warfare into a grinding nightmare of attrition and death. Stalingrad had proven this truth in the bloodiest way imaginable. Thousands of German soldiers had died, clearing rubble-filled streets, step after step, corner after corner, each one a potential death sentence. The Soviets waited like spiders in the shadows, positioned just out of line of sight, knowing that German soldiers would eventually have to expose themselves. When they did, bullets found them. But what Hartman was witnessing today promised to change everything. This device, this Krummlauf, as Weininger called it, could fire bullets around corners while keeping the shooter completely sheltered behind concrete and steel. The curved barrel system channeled projectiles through a precisely engineered bend, sending them on a path that no conventional weapon could achieve. Bullets traveling at 685 meters per second would follow that engineered curve and strike targets the shooter couldn't even see. German engineering had just rewritten the rules of ballistics itself. Hartman adjusted his field glasses and studied the sprawling facility before him. The Ryan-Metall Borsig proving ground looked like a landscape from another world. Concrete barriers, steel targets, blast craters scattered across the terrain like evidence of 1,000 experiments. This was where Germany's most ambitious weapons programs came to life. 2,000 rounds fired daily from 20 different positions created a constant symphony of destruction that had become the heartbeat of German innovation. The September air carried the sharp bite of autumn mixed with something else, the acrid smell of cordite and hot metal that seemed to hang permanently over the facility. Pine forests surrounded the proving ground like silent witnesses to the engineering miracles taking place within. Everything about this place spoke of precision, dedication, and desperate ambition. The urgent telegram from Wehrmacht High Command remained crumpled in Hartman's breast pocket. Urban combat had become Germany's greatest tactical nightmare. In Stalingrad's rubble-choked streets, every corner was a death trap. Soviet defenders positioned themselves where German soldiers couldn't reach them without exposing themselves to withering fire. The doctrine was simple in theory, suicidal in practice. Step around the corner, find the target, fire. But by the time a soldier stepped around, the Russians were already waiting. Hartman remembered conversations with men who had survived that urban hell. Obergefreiter Miller, a veteran machine gunner, had explained the deadly mathematics with grim precision. Every time they cleared a building, they lost men to positions they couldn't see. The Russians understood the advantage of waiting around corners, turning the soldiers' own need for survival into a tactical disadvantage. How do you kill an enemy you cannot see without exposing yourself to their fire? Physics said it was impossible. Military necessity said it was required. That contradiction had haunted Hartman's methodical mind for months. Chief Engineer Karl Warninger approached with the confident stride of a man who had spent years proving skeptics wrong. Since 1938, he had transformed from an automotive engineer into a weapons innovator. His team had produced nearly 20 different systems that had given German forces advantages across multiple theaters. But the Krummlauf represented something different, something that challenged the fundamental laws of how bullets traveled. Weininger's hands bore the scars of countless prototypes. His eyes held the gleam of an inventor who had never encountered a problem he couldn't engineer into submission. He gestured toward the wooden crate containing the prototype. "Physics says bullets travel in straight lines," Weininger announced, his voice carrying the authority of a man who had challenged conventional wisdom and won. "We are about to change physics." The curved barrel attachment resembled science fiction made tangible. The system represented months of intense development work. Weininger's engineering team had started with a 20mm trough that guided projectiles around corners through a curved channel. Early tests showed promise, leading them to develop rifle-bent barrels that could handle the STG-44's standard 7.92mm ammunition. The mathematics were elegant in their simplicity. Bullets exiting the rifle's muzzle at 685 meters per second would follow the engineered curve and emerge to strike targets in tactically impossible positions. German soldiers could engage enemies around corners without exposure, revolutionizing the entire nature of urban warfare. The infantry prototype featured a 30-degree bend. The barrel measured 14 inches total, 4 inches of straight barrel, 5.5 inches of precisely curved section, and 4.5 inches of straight exit. A periscope sight mounted above the curved section allowed soldiers to aim while remaining completely protected behind cover. Weininger's calculations showed the device could withstand 6,000 rounds of continuous use, more than enough to equip every STG-44 in Wehrmacht service. Obergefreiter Hans Müller prepared for the day's demonstration. He had survived Stalingrad's urban nightmare and volunteered for this dangerous assignment after learning about the Krummlauf's potential. Müller moved with practiced efficiency as he attached the curved barrel system to his familiar rifle. The marriage of proven firearm and revolutionary attachment represented German engineering at its most ambitious. Müller positioned himself behind a concrete barrier completely hidden from the target array set up around the corner. Through his periscope sight, he could observe targets that would have been impossible to engage with any conventional weapon. His breathing steadied. His finger rested on the trigger. The first shot cracked across the proving ground. Through his field glasses, Hartman watched the bullet emerge from the curved barrel and strike the primary target with devastating accuracy. The impossible had become reality. Successive shots demonstrated the system's tactical brilliance. Müller engaged targets at varying ranges, each bullet following its engineered curve to find enemies beyond direct line of sight. The grouping at 100 meters measured 35 by 35 centimeters. Excellent accuracy for close-range urban combat, exactly what this weapon was designed to achieve. Weininger's calculations appeared vindicated. German engineering had solved urban warfare's deadliest problem through superior precision and innovative thinking. Yet Hartman's trained eye noticed troubling details he couldn't dismiss. Bullets emerged from the curved barrel, showing signs of deformation. Some appeared damaged, their copper jackets scraped and torn by the violent redirection through the bend. The barrel itself grew hot more quickly than standard weapons, suggesting unusual stress concentrations within the steel. But the weapon functioned, targets fell. Wehrmacht High Command demanded results, not perfection. Weininger's confidence remained unshaken as he explained the system's broader applications to Hartman. Plans called for multiple variants, 30-degree, 45-degree, 60-degree, and even 90-degree versions to address different tactical situations. The 90-degree version would revolutionize tank warfare by allowing vehicles like the massive Elephant tank destroyer to engage infantry at close range, solving that vehicle's fatal flaw of having no defensive machine gun. 500 tank mounts were already on order, with Zeiss producing 1,500 periscope sights for delivery by January 1945. As the morning's tests concluded, Hartman felt the weight of history pressing against him. The Third Reich was losing ground on every front. Each week brought news of tactical defeats, strategic withdrawals and and mounting casualties. Germany needed technological advantages to offset its numerical disadvantages. The Krummlauf represented exactly the kind of innovative thinking that could shift the war's trajectory. His report would either validate German engineering genius or doom a project that promised to save thousands of German lives. Standing in the proving ground's afternoon shadows, Hartman began composing his preliminary assessment in his mind. The weapon worked. Physics had been conquered through superior German engineering. What neither Hartman nor Warninger could know was that physics always collects its debts. The Krummlauf's reckoning was already written in the mathematics of metallurgy and ballistics, equations that no amount of German precision could overcome. October brought intensified activity to Ryan-Metall Borsig. Warninger's engineering team had expanded dramatically to accommodate the Krummlauf's ambitious development schedule. Workshops hummed with constant activity as machine tools shaped steel into geometries that defied conventional gunsmithing wisdom. The sound of precision drilling echoed through the facility. Engineers crafted barrel components with painstaking attention to detail, each curved section hand-fitted and tested to tolerances that pushed German manufacturing capabilities to their absolute limits. Warninger moved through his domain like a conductor, orchestrating a complex symphony of innovation. His 200 engineers had been divided into specialized teams, each focused on perfecting different aspects of the revolutionary system. The metallurgy group worked to identify steel alloys that could withstand the extreme stresses of redirecting high-velocity bullets. The optics team collaborated with Zeiss engineers to develop periscope sights that could function in the harsh environment created by muzzle gases and battlefield debris. The production planning group calculated manufacturing requirements for a weapon system unlike anything in Wehrmacht inventory. The 30-degree infantry version had evolved into an elegant solution to urban warfare's tactical nightmare. Engineers had added strategically placed vent holes along the curved barrel section to relieve gas pressure that would otherwise stress the steel beyond acceptable limits. The venting system required precise calculation. Too few holes and the barrel would fail catastrophically. Too many, and the weapon would lose velocity and accuracy. Warninger's team had found the optimal balance through hundreds of test firings, each shot carefully monitored and documented with meticulous precision. Dr. Friedrich Busch arrived from Wetzlar with prototypes of the specialized periscope sight system that would make the Krummlauf tactically viable. The optical engineer had spent weeks perfecting a 1.5 times magnification system capable of withstanding the violent environment created by the curved barrel's operation. The sight featured a triangular shield designed to protect the delicate mirror system from hot gases and debris expelled through the barrel's vent holes. Busch's precision craftsmanship represented German optical engineering at its finest, each sight individually calibrated to work with specific barrel configurations. Major Ernst Weber had joined the project as Rheinmetall's liaison with Wehrmacht testing protocols, bringing military oversight to the engineering innovation. The retired physics instructor brought scientific precision to an increasingly intricate technical problem. Weber's strength lay in mathematics, allowing him to analyze the ballistic forces that bullets encountered while traveling through the weapon's curved sections. His computations exposed stresses that conventional straight-barrel designs never faced. Yet the engineering team had already developed workable answers to each theoretical concern Weber raised. The 90-degree tank-mounted variant posed distinct difficulties requiring specialized approaches, designated the P model for armored deployment. This design would enable tank crews to defend against close infantry threats without becoming exposed to counterattack. The massive tank destroyer had shown it could be defeated by infantry assault teams precisely because it lacked adequate close-range defensive weapons. Soviet tank hunting squads approached these 70-ton machines from concealed angles, employing magnetic explosives and demolition charges to immobilize tracks and blind vision systems. The curved barrel system would address this critical vulnerability by equipping tank crews with protective firepower at close range. Installing the mechanism in tanks created mechanical complications that ground-level versions simply didn't encounter. The tank's armored body needed specialized attachment points capable of absorbing recoil while preserving the alignment required for reliable accuracy. The engineering group developed a mounting framework that worked with the existing tank commander's position, allowing operators to fire from behind the vehicle's protective steel. This sophisticated setup demanded considerable crew preparation, though the battlefield benefits justified the training commitment. Controlled testing proceeded in simulated combat settings, avoiding unnecessary exposure to personnel. Officers observed the evaluations with growing confidence in German manufacturing skill. The ground-based model repeatedly showed acceptable precision at distances reaching 100 meters, sufficient for the tight spaces where corner engagement capability would matter most. Soldiers could strike adversaries positioned at building corners, window openings, and rubble piles while staying protected from return fire. The psychological influence proved equally valuable as the tactical benefit. German troops had become familiar with the grim arithmetic of street fighting, where attacking concealed opponents required accepting deaths as unavoidable. This new system offered something revolutionary, a way to wound or kill enemies while remaining behind cover. Morale improvements were swift and obvious as soldiers grasped its life-protecting possibilities. Military leadership accelerated manufacturing plans after grasping the strategic potential. Orders specified 500 tank-mounted units with commitments to provide 1,500 infantry versions by early January 1945. The schedule was demanding yet realistic given manufacturing output and the Reich's pressing requirement for fresh tactical advantages. The engineer's established reputation for producing complex weapons on demanding timelines made him the natural choice to manage the expanded effort. Weber's initial concerns remained mostly academic, as actual field trials kept validating the system's core performance. His mathematical predictions indicated barrel life problems stemming from extreme redirection forces acting on high-speed ammunition, yet the preliminary trials suggested his calculations were unduly cautious. Tubes endured hundreds of discharges without detectable damage marks, while accuracy remained unchanged through prolonged shooting sessions. German steel manufacturing appeared sufficient for the unprecedented demands the curved barrel system imposed. Germany's worsening military circumstances throughout all theaters intensified pressure on every phase of the program. American and British forces had established positions in France, while Russian forces advanced without pause across Eastern Europe. Wehrmacht command desperately required tactical breakthroughs capable of neutralizing their numerical disadvantage and reclaiming battlefield superiority. These experimental weapons symbolized hope that German technical excellence might still alter the conflict's trajectory. The engineer prepared his status report with meticulous attention, recording each aspect of creation and evaluation. His precise approach demanded absolute honesty, yet the stress to validate German achievements created contradictions in his professional judgment. The mechanism accomplished its intended function, meeting tactical requirements that standard firearms could not provide. Cosmetic problems, including ammunition distortion, appeared trivial compared to the unprecedented effectiveness this system demonstrated. His confidence reached its height as spring arrived, with announcements of increased manufacturing orders. Wehrmacht officials journeyed to facilities to witness operational demonstrations and confirm production schedules. The curved barrel concept had progressed from theoretical proposal to functional prototype in merely 5 months, showcasing German industrial prowess and creative engineering. Roughly 20 distinct combat innovations had originated from this facility since mid-1944, yet none appeared capable of reshaping battlefield tactics as fundamentally as this invention. The former academic and Weber both comprehended mathematical principles that engineering enthusiasm could not overcome, but organizational backing for the initiative had become irresistible. Germany's fighting men needed tactical advantages, military commanders demanded breakthrough solutions, and German manufacturing had delivered precisely what the Reich demanded. This curved barrel weapon represented the pinnacle of German technical achievement when energized and properly equipped. Spring's progression brought curved barrel assemblies prepared for deployment and projected to redefine close-quarters combat through German engineering excellence. What stayed concealed beneath the facade of technical achievement were fundamental physical principles that no engineering ingenuity could ultimately surpass. Late winter brought troubling observations that the engineer's systematic approach could no longer overlook. Extended evaluation periods disclosed cracks developing in barrel components much sooner than the engineering projections anticipated. Fine fractures initiated at the curve's highest point, where ammunition experienced maximum redirection stress. propagating through metal, resembling webs of deterioration. The engineer meticulously recorded each visible defect through photography, his comprehensive assessments revealing how physical constraints were surpassing German manufacturing capabilities. Despite dedicated efforts, the projectiles themselves presented increasingly disturbing evidence. High-velocity imaging recorded ammunition departing the curved sections showing varying degrees of structural breakdown. Certain projectiles kept their outward form but displayed severe surface damage where outer layers had been scrubbed away by extreme friction against interior metal. Others left the barrel partially destroyed, their interior metal separated from exterior casings during the severe redirection experience. Most alarming were projectiles that split completely at the coupling ring, joining bullet segments, creating a spray pattern resembling shotgun dispersion rather than a concentrated strike. The mathematician's theoretical predictions were materializing as practical catastrophe with disturbing frequency. His mathematical framework had anticipated these specific failure mechanisms, though institutional pressure had overridden scientific judgment. The retired professor now documented real-world consequences of dismissing established ballistic principles. Ammunition moving at 685 meters per second could not navigate sharp curves without forfeiting structural soundness in methods German production methods could not rectify. The chief engineer confronted these findings with the unwavering determination characterizing his professional lifetime. Each previous obstacle had ultimately surrendered to superior German manufacturing and creative solutions. The fracturing sections represented technical problems demanding technical answers. His personnel immediately pursued reinforced tube designs, investigating substitute metal compositions and redesigning the angle configuration to minimize stress concentration regions. Supplementary openings were incorporated to discharge internal pressure. Metal thickness around the curve was expanded to distribute stresses more uniformly. Every design adjustment demonstrated German engineering's rejection of surrender. Military pressure had multiplied far beyond anything the engineer had previously encountered in his career. Germany confronted territorial losses on every front, with Western armies pushing eastward through France and Soviet forces pressing southward from Eastern Europe. National survival depended on technological breakthroughs capable of neutralizing overwhelming enemy numbers and recovering tactical control. These experimental systems symbolized the possibility that technical superiority might still determine final victory. Disappointment represented professional catastrophe. Beyond professional stakes, failure meant abandoning the fatherland during its moment of maximum peril. Field reports underwent gradual yet deliberate alterations as they progressed through military administration. The 90-degree variance operational durability of 300 rounds transformed into acceptable performance for assigned purposes. The 45-degree version's 160-round lifespan became described as suitable for particular specializations. The hazardous projectile fragmentation creating zones of erratic ammunition trajectory was reframed as enhanced close-range capability against human targets. Physical findings were being converted into bureaucratic acceptability. Using strategically selective description, the engineer experienced internal conflict between scientific accuracy and professional obligation. His systematic thinking demanded complete truthfulness in all documentation, yet his supervisors sought confirmation of German manufacturing supremacy. This ethical conflict deepened as he confronted an agonizing realization. Honest assessment might terminate an undertaking that could preserve German personnel, whereas misleading information could endanger the combatants ultimately depending on this equipment. Military discipline had trained him to execute directives without resistance, yet his moral compass demanded recognition of the curved barrel weapon's serious shortcomings. Germany's deteriorating battle position complicated every option. Military authorities desperately sought technological innovations, enabling renewed battlefield dominance. The fighting in the Eastern Territories devoured personnel and supplies at impossible rates. Meanwhile, Western threats escalated as Allied numbers increased. Every technology promising battlefield advantage required serious consideration, regardless of inherent dangers to operators. Armed conflict had decreased to mathematical simplicity. German survival required optimizing every resource advantage. A veteran non-commissioned officer came back from extensive operational assessment, carrying direct knowledge of the curved barrel system's practical performance. The experienced soldier's observations conflicted with approved assessments, with discomforting directness. Performance proved satisfactory for quick exchanges, but deteriorated rapidly with extended activity. Metal fracturing generated perilous pressure ruptures, potentially wounding those handling the system. Ammunition fragmentation restricted useful distance to immediate proximity, minimizing practical battlefield applications. Most troubling remained the unreliable projectile performance. Soldiers possessed no certainty regarding whether impacts would strike intended recipients or instead produce uncontrolled fragmentation patterns. The manufacturing facility had developed approximately 20 different combat applications since mid-1944. Each represented attempts to engineer battlefield dominance through technical innovation. The curved barrel innovation occupied special standing in this collection since it resolved a particular combat scenario remaining unsolvable through conventional approaches. Close quarters fighting's corner engagement issue lacked alternative approaches, rendering the curved barrel mechanism indispensable despite its technical problems. Professional ambition joined military requirement to produce unstoppable momentum. The mathematician's position as technical representative became progressively problematic as his scientific education conflicted with organizational demands. His mathematical background generated comprehensive comprehension of pressures involved in redirecting fast ammunition through sharp angles. The mathematical principles regulating projectile behavior resisted compromise, and engineering solutions could not change fundamental nature. Physical regulations functioned independent of patriotic sentiment or organizational expectation, establishing permanent constraints that engineering creativity could not overcome. The enhancement schemes demanded enormous expenditures as manufacturing worked to resolve difficulties inherent to the fundamental design. Alternative curved geometries underwent examination to decrease pressure concentrations. Different metal substances received evaluation for strength and durability. Tube cross-sections were expanded to distribute forces uniformly. Each modification tackled isolated aspects, while disregarding the core problem. Ammunition could not be redirected through sharp curves while preserving structural integrity through techniques available to German manufacturers. The engineer's inner struggle intensified through field experiences, revealing the complete extent of operational restrictions. Official documents might honestly acknowledge these constraints, potentially cancelling an undertaking representing months of strenuous labor, or they might downplay concerns, permitting a defective system to reach military personnel dependent upon it. The determination between technical honesty and professional commitment had evolved into a choice between philosophical standard and actual consequences affecting German combatants. Summer months passed in persistent redesign efforts, continuous assessment cycles, and progressively imaginative language describing test findings as German industry struggled against physical limitations, transcending superior manufacturing precision. The curved barrel mechanism persisted in functioning, yet its flaws were becoming apparent to individuals prepared to acknowledge inconvenient facts about the distance between German technical ambition and unchanging physical principles. Early September brought authorized commencement of manufacturing at industrial production centers. Regardless of concerning evaluation information, the mathematician consistently catalogued with academic rigor. Military procurement sanctioned preliminary deliveries of 500 tank versions. The momentum propelling the curved barrel initiative had become unchangeable, sustained by Germany's collapsing strategic circumstances and requirements for any breakthrough capability affecting combat effectiveness. Images started circulating in military instruction materials, displaying German personnel employing the curved barrel equipment from protective positions. The photographs had been meticulously composed to showcase the weapon's groundbreaking potential while carefully avoiding any mention of its serious drawbacks. One engineer supervised the entire production effort with the same precise, systematic approach that had earned him recognition as Ryan-Metall's finest technical mind. Each curved barrel demanded painstaking individual construction, with experienced machinists hand-assembling parts to specifications that stretched German manufacturing beyond what was normally considered possible. Creating bent barrels strong enough to survive the brutal forces of actual combat proved exponentially more difficult than anyone had initially predicted. Thorough testing of every single component became mandatory under proper quality control standards, yet the mounting pressure to deliver forced decisions that would never have been tolerated during normal peacetime operations. The tank-mounted versions started arriving with Wehrmacht armored divisions in September, paired with comprehensive technical instruction that stressed correct operating procedures while deliberately downplaying concerns about durability and service life. Elephant tank destroyer teams trained intensively on the 90-degree variant, learning how to strike infantry targets at very close distances while staying protected from counterattack. The tactical benefit became immediately obvious. These massive vehicles could now defend themselves against the swarming infantry that had made them dangerously vulnerable despite their thick armor. Initial reports from the field suggested the curved barrel system was working exactly as intended. Tank commanders reported killing Soviet infantry teams, with the bent barrel letting them strike enemies hidden in spots where straight guns couldn't possibly reach. The morale boost proved just as valuable as the tactical advantage, with crew confidence climbing noticeably as tank warfare's deadly calculations suddenly swung Germany's way. Wehrmacht tactical planning began incorporating corner-shooting maneuvers that previous weapons simply couldn't perform. Hartman received his first combat report in October, stamped with the urgent security classifications that marked highly sensitive operational material. Even with its guarded language, the document's true meaning was impossible to hide. Extended combat use was exposing the complete catastrophe of the curved barrel design in ways that laboratory testing had only hinted at. Barrels were exploding violently during actual fighting, spraying glowing hot metal fragments toward crew members with absolutely no protection against shrapnel from their own gun. The venting holes that the engineers' team had designed to release pressure were creating dangerous backblast that could severely wound operators. Superheated gases and sharp metal pieces erupted from the vents with violent unpredictability, turning the system's protective features into serious threats. Even more frightening was the consistent shattering of bullets at the rifling section, producing fragment patterns like a shotgun blast that endangered everyone standing near the weapon's opening. The curved barrel gun had transformed into something deadlier to its crew than to enemy troops. A soldier's detailed combat account provided unvarnished truth that contradicted what official paperwork claimed. The experienced Wehrmacht soldier had used the infantry model during house-to-house combat in East Prussia, fighting Soviet forces pushing through German positions. His personal testimony described a weapon that functioned acceptably during quick firefights, but started breaking down predictably after relatively brief use. The bent barrel had developed serious cracks after roughly 200 rounds, producing gas leaks that made further shooting dangerously risky. When the barrel finally shattered completely, metal shards came frighteningly close to striking Muller and two other soldiers nearby. The mathematical forecasts made by the physics experts were now becoming brutal operational reality. The physicists' models had precisely calculated how the intense ballistic forces from driving fast-moving bullets through sharp angles would cause failure. The 70 to 80% bullet breakup rate at the forcing cone was happening precisely as physics demanded, generating shotgun-style fragmentation that cut effective range down to extremely close distance, while simultaneously threatening friendly soldiers. The laws of nature were exacting their payment with compounding consequences. The chief engineer's reaction to these combat reports revealed the engineering overconfidence that had driven the program from the very beginning. Each breakdown was viewed as merely another solvable challenge requiring further tweaks rather than proof of basic design problems. His group started working immediately on reinforced barrel styles, testing new vent hole arrangements, and examining alternative curved shapes. Extra steel reinforcement got welded onto high-stress locations. The triangular shields shielding the sight mounts grew bigger to stop hot gas blasts. Each new attempt showed German engineering's stubborn refusal to accept defeat. The information control effort commenced, with careful rewording of combat reports passing through Wehrmacht bureaucracy. Fighting effectiveness summaries were rewritten to highlight successful shots while removing talk of equipment problems. Injury numbers got classified as confidential information that couldn't be shared without risking operational security. The dangerous fragmentation threat was repackaged as an intentional design feature, delivering better results against personnel at extremely short range. Technical facts were being deliberately transformed into acceptable institutional narratives. Hartman discovered himself entrenched in this reporting and information management scheme. His reputation for careful, precise analysis made him the logical choice for reviewing adjusted reports. His personal crisis deepened as he recognized that truthful documentation would embarrass Wehrmacht leadership for deploying a faulty system, while falsifying reports would allow a dangerous situation to persist for German troops depending on accurate information for their lives. The conflict between loyalty to the institution and devotion to professional honesty had shifted into a conflict between theoretical ideals and real survival for personnel who trusted technical accuracy. Germany's worsening circumstances throughout autumn 1944 intensified every difficult decision. Red Army forces were sweeping through Eastern European territory, while Western allies advanced through Western Europe toward Germany's border. Wehrmacht command desperately sought tactical breakthroughs that might compensate for being outnumbered and regain control of battlefield advantage. The curved barrel gun represented precisely the kind of innovative breakthrough that might change the war's trajectory, making its technical defects seem trivial compared to its operational possibilities. Manufacturing continued through early 1945, despite accumulating proof of serious design problems. The project had achieved institutional momentum with its own driving force, fed by the Reich's urgent hunger for revolutionary weapons, capable of changing Germany's increasingly hopeless predicament. Fewer than 1,000 weapons actually entered field service before production finally ceased, though the psychological and tactical damage to German operations had already occurred. The closing field report arrived at Hartman's workspace during March 1945. Its security markings communicated the report's sensitive classification. A panzer crew took injuries from fragments of their own curved barrel gun throughout a fighting withdrawal near the Oder River. The bent barrel system ruptured explosively, ejecting incandescent steel shards straight into the tank's interior compartment. The crew survived, yet their wounds offered conclusive evidence that the Reich's greatest tactical innovation had become a destructive danger to the very soldiers it was meant to protect. The fantasy of German engineering supremacy through physics was expiring gradually, one catastrophic barrel rupture at a time. By August 1945, the Ryan-Metall Borsig testing facility lay abandoned for the first time in 6 years. The relentless explosions from test firing that had marked Germany's desperate quest for world-changing weapons had fallen silent, replaced by the methodical work of American technical experts cataloging captured German hardware. Colonel H.A. Quinn walked through the silent grounds with unhurried, measured steps of a seasoned technical investigator. His experienced eye examined Germany's engineering achievements scattered across testing concrete that still displayed burn marks from thousands of trial firings. Quinn, standing at Aberdeen Proving Ground, centered on his capacity to distinguish authentic performance from propaganda, a proficiency refined through years examining American systems alongside captured enemy weapons. His meticulous evaluation method gained respect from his team for his commitment to judging foreign technology fairly rather than dismissing it simply for coming from an enemy. The curved barrel specimens his crew had recovered from multiple German locations represented exactly the technological mystery demanding serious objective examination instead of patriotic rejection. The American analysis started with detailed photography of each curved barrel component. Quinn's team shot comprehensive pictures from every angle, recorded precise measurements with calibrated gauges, and documented all the different fixes that German technicians had attempted while struggling with ongoing troubles. The evidence of desperate, improvised problem-solving showed in the assorted vent arrangements, strengthened barrel sections, and changed mounting brackets that proved constant efforts to fix core problems via step-by-step modifications. Aberdeen's firing range offered control that German field testing lacked. Quinn's crew readied for systematic testing using standardized American ammunition. eliminating factors that could have changed German outcomes. The 30-degree infantry model was picked for complete testing. Its basic configuration made it best for establishing foundational performance. High-speed recording devices were arranged to monitor projectile path through the curved section. The opening shots backed up Weber's calculations with perfect accuracy. Projectiles departed the bent barrel badly misshapen, their metal casings scraped and damaged by severe scraping against the barrel's interior. High-speed video demonstrated the savage reality of trajectory bending as ammunition moving over 2,000 feet per second was twisted through sharp angles that exceeded what ordinary ammunition could withstand. The sophisticated mathematics that justified the program got crushed by the harsh reality of material failure. Thorough testing displayed performance that German files had concealed through deliberately vague descriptions. The actual working life lasted just 300 rounds for the 30-degree design, with cracks appearing dependably at the curve's center, where redirecting power peaked. The 45-degree design survived only 160 rounds before producing gas leaks that became too hazardous. The most disturbing finding was the consistent fracturing of projectiles at the forcing cone, producing shotgun-type patterns completely unlike focused gunfire. Quinn's team catalogued each breakdown with photographic accuracy, compiling a thorough documentation of the curved barrel system's limitations. His assessments would give American commanders comprehensive knowledge of German technical skills while explaining the dangers of following engineering approaches that ignore elementary physics. The curved barrel demonstrated German ingenuity at its most daring and most foolish, revealing both the Reich's technical sophistication and its stubborn refusal to face inconvenient facts. Accounts from captured Wehrmacht officers added human perspective to the technical failures Aberdeen had demonstrated. Major Klaus Hartman sat facing Quinn in a simple interview space, his careful personality showing in his thoughtful, methodical way of speaking. This former Wehrmacht ordnance officer's statements supported everything American testing had uncovered. The curved barrel had never delivered results it promised, despite frantic efforts to engineer fixes to fundamental problems. Hartman's testimony showed the institutional pressures forcing the program beyond reasonable boundaries. The Reich's collapsing military situation had generated frantic need for technological miracles that could reverse Germany's fortunes. Wehrmacht leadership demanded tactical advantages to overcome numerical disadvantages, making every promising development impossible to reject, regardless of technical problems. The curved barrel weapon had symbolized confidence that German technical excellence could still affect how the war concluded. The human consequences of engineering arrogance emerged as Hartman detailed the moral conflict that had tormented his final Wehrmacht months. His professional responsibility demanded clear reporting of the weapon's serious hazards, yet military duty necessitated supporting German innovation. The struggle between objective truth and practical consequences for German fighting men had damaged his orderly thinking, forcing him to pick between scientific fact and military obligation. Another officer's account exposed the engineering psychology maintaining the program despite accumulating proof of primary flaws. The senior technician stayed convinced that German precision could conquer any physical challenge through superior design and manufacturing skill. His statements revealed a professional environment treating physics as difficulty requiring conquest instead of genuine constraint. Reich obsession with miracle weapons had produced expectations no engineering skill could possibly fulfill. The academic background offered the clearest comprehension of why catastrophic failure happened. The former university instructor outlined his futile efforts, cautioning Wehrmacht superiors about the mathematical realities embedded in the curved barrel design. Mathematical predictions had precisely forecasted breakdown methods based on ballistic science that institutional pressure couldn't override. Natural physical laws worked independent of national commitment or engineering brilliance, producing constraints superior German skill couldn't eliminate. Quinn's complete analysis blended ballistics testing with officer statements for thorough comprehension of development and eventual failure. The investigation acknowledged German technical quality while revealing the destructive consequences of pursuing technical innovations without respecting physical boundaries. The curved barrel device had devoured substantial resources while generating a system threatening its operators as much as intended targets. American military command received Quinn's evaluation with expert regard instead of smug satisfaction. Germany's misstep provided instructive lessons regarding the connection between engineering aspirations and physical truth reaching across all nations. American weapons planning could equally gain from recognizing how organizational pressure and unrealistic optimism had produced a system disregarding ballistic science. The implications transcended merely wartime military concerns to encompass deeper questions about scientific truth in weapons production. The curved barrel's catastrophe illustrated that even maximum technical excellence couldn't bypass natural laws through superior accuracy or revolutionary innovation. Certain obstacles need different strategies rather than superior craftsmanship, and the deadliest systems sometimes threaten their own operators. Quinn's analysis wrapped up recognizing that Germany's curved barrel system embodied both the heights and depths of Wehrmacht weapons creation. The organizational environment producing impressive achievements like the STG-44 assault rifle had simultaneously created dangerous delusions like the curved barrel. The distinction wasn't in technical capability, but in readiness to acknowledge unpleasant facts about limits and aspirations. In halting English, Hartman captured the tragedy with stark simplicity. We believed we exceeded physics. Physics prevailed. The inscription on German engineering's downfall was carved in warped steel, and fragmented bullets spread across Aberdeen's testing grounds. An eternal testament that some contests cannot be conquered through greater precision or engineering innovation.